So thank you very much, and welcome to this presentation. We'll present the paper titled Decision Mining with Time Series Data Based on Automatic Feature Generations. And for the next 20 or so minutes, I will start by introducing a running example to show why this is an important issue, why this is a challenge. Then I will go a little bit more into depth about the approach we introduced in the paper called EDT-TS, standing for Extended Decision Tree Time Series. And I will try to elaborate the approach according to the line of thinking while developing the approach, so stemming from a problem in the decision mining domain, going a little bit into the time series analysis part, and then how to integrate everything back into decision mining. Of course, then I will talk a little bit about the evaluation. We were using one synthetic data set as well as one real use case from the manufacturing domain. And last but not least, I will talk a little bit about the limitations of the approach as well as what my current and future work include. So let's start off by introducing an example. So the running example is from the logistics domain, and let's first have a look at the process model here. This is a process model about the transportation of temperature-sensitive goods. So we start off the process by loading cargo onto a transporter, then the transporter is moving towards a customer, so towards a destination, and during that, the temperature is measured continually. As soon as we arrive at the destination, we have a decision to make. Either we can give the goods to the customer because they are fine, or if the temperature was too high during the transportation process, the goods may be spoiled and we have to discard them because they cannot be safely transferred to the customer. So that's the focus of our research, basically this decision point. And we're asking, okay, what is the decision rule underlying this decision point? And we quickly notice we cannot just take one temperature measurement by its own, because we want to have a look at the whole measurement of temperature to see was the temperature above a certain degree for a longer period of time, so that we are certain the goods are not are spoiled and we cannot transfer them anymore. So we have also time series examples of an instance where the goods are not okay anymore, they have been spoiled, and one where the goods are okay, and we can see that for the instance where they are not okay anymore, the temperature measured higher for way more measurement points than for the instance where the goods are still okay. So we assume that the underlying decision rule at this point is if the temperature is greater than 25 degrees for more than 3 measurements, then we have to discard the goods. However, here we run into the first problem, the first challenge, because current decision mining algorithms are not able to work with time series data like that. They are only able to work with singular measurement points, for example, the last measurement or the second to last measurement, but not view them together as a whole. So we tried it, we generated a synthetic data set of about 5,000 instances, and we put it through a standard decision mining algorithm, and the resulting rule can be seen here in the second line, and it's basically if the temperature is above 25.5 degrees, then it is not okay. And we can see here we have a reduction of information here that's basically led to a rule that is not accurate anymore, because that's just not the baseline decision rule is kind of similar, but it just doesn't take into account all the information that we have, which can also be seen by the accuracy, which is only at 59%, so basically a little bit better than guessing. So that's the research gap. That's what we wanted to work on. We wanted to enable the automatic discovery of comprehensible decision rules from time series data. And that's not only interesting for logistics, for the running example, but can be interesting for a multitude of different domains. So basically, every domain where we have some kind of sensor data, for example, because sensor data is time series data. So we can look at manufacturing, where we have lots of different sensors involved. We have healthcare, tourism, and a multitude of other domains where that could lead to more information that we can work with and to better and more accurate rules. The challenges here already mentioned. So currently decision trees or decision mining techniques in general cannot work with time series data as a whole. Also, there is one approach already in literature where the authors wanted to combine decision mining and time series data. However, that was more of an interactive approach, and we wanted to specifically focus on an automatic approach. And also, a third challenge or a third goal was that the results should be interpretable. So we don't want a black box approach. We want a result where we have a decision rule that can be read by users, by domain experts, and can be checked for the correctness. So we want to provide more transparency as a whole. We started by looking at time series literature, and one very interesting aspect is patterns. How can we characterize time series by the patterns that occur? And so we identified a couple of interesting patterns. For example, stationary pattern is where the mean of a time series stays basically constant and the values just fluctuate around that mean. We have a trend where the values decrease or increase continually. We have a seasonal pattern where we have this kind of fluctuations, but they are reoccurring in an ordered manner. We have a shift where the values decrease or increase abruptly, but then stay at kind of a new mean. One additional pattern that we identified and added are thresholds, which are kind of similar to shifts, but instead of arriving at the new mean, the values go back to the mean they had before the shift. Of course, we can have combinations of all of these patterns to create even more complex and interesting patterns for time series. If we go back to the running example, we could identify this as having a threshold pattern. So here we have the 2 spikes, but for the running example, that would be 3 or more spikes over 25 degrees to identify a not okay instance. Yeah, that's already a pretty interesting thing, but however, we are still missing an approach on how to detect these patterns in event logs, in our data, and how can we phrase the according decision rules appropriately. So the next step was to look a little bit more into feature generation. So feature generation basically means we take the whole time series and apply some form of calculation on top of this time series to create a new feature, and this helps us to reduce the dimensionality and the complexity of the whole time series, but still allows us to keep information. For us specifically, the challenge was also that we don't want to reduce the dimensionality by such an extent that we are losing the interpretability, so we still want to keep as much of the information that we can, so it can still be interpreted by humans at the end of the approach. So in total, we identified 3 kinds of new features that can be generated to help us identify all of the patterns mentioned beforehand, and also additional characteristics of time series that could be relevant for mining decision rules. So first off, we have global features, which can be seen in the first image. That's basically we take the whole time series and calculate one value on top of that. For example, we see here in the image the slope could be calculated of a time series, but also the mean, of course, or some more complex values that, for example, a Fourier transform or autocorrelation. The next thing is pattern-based features. Here we have a closer look at the exact values that occur in the time series, as well as the distribution of values. So as an example, we here have a histogram, so we can see exactly which values occur and how often they occur in the time series. Of course, there are potential for a lot of different pattern-based features, so we could also look at value ranges, how often do values occur in these ranges, or look at certain thresholds, so how often does a value occur that's bigger than 20, for example. So there are a lot of possibilities. And last but not least, we have interval-based features. So the first two features are applied on top of the whole time series, and the interval-based features are applied on subsequences. So we take the time series, split it into different sub-intervals, and then we apply some kind of feature calculation on top of these subsequences. So that, of course, allows us to have a much finer granularity analysis of the time series. Yes, and these kinds of new features allows us now to formulate some decision rule patterns. So in total we have 4, but only 3 are new. So the first decision rule pattern is the baseline decision rule pattern. So the kind of decision rule that we know from literature, how most decision rules are formulated. And it's basically of the form, if a variable compares via an operator to a constant in a certain way, then we can label it as a certain class. So the example would be if age is below or equal to 16, then a children's discount can be applied. Then we move forward to the new decision rule pattern. So the second one involves global features. So we take a global feature, apply it onto a variable, and then compare it to a constant as well, which then is decisive for the class label, basically. An example would be if the mean of the temperature is above 30, then we have to increase the cooling. So that's not really a class label, but rather the path a certain instance is taking in this instance. The third decision rule is including interval-based decision rules. And we have a feature applied on a variable in a certain interval. So an example would be if the percentage change of lactic acid is above 10% in the first interval, then we have to stop the treatment. So that's an example from the medical domain. And last but not least, the fourth decision rule pattern includes pattern-based decision rules. And it is of the form, if a variable compares to a constant for a certain number of times or in a certain time range, then we have a specified class. Another example from the medical domain would be, that's a true example for diagnosing preeclampsia in pregnant women, and it's if the weight gain is greater than 1 kilogram for 3 times, so for 3 consecutive measurements, then a patient has to be admitted. So we can also see here that we have a lot of application potential in medical domains as well. Yeah, so let's take all of that and put it together for the whole approach. The approach can be split into 3 stages. First one is pre-processing, where we read and prepare the data set, and then we look at which data elements are potentially time series elements, and then we take these called candidate variables and apply the feature generation algorithms on top of that. So we create global features. Here we use an existing library, and then we also create pattern-based features as well as interval-based features, where 2 new algorithms were implemented by us. And then we use all of these newly generated features to build a decision tree. Basically, every kind of decision mining technique could be used. For this, we used a card decision tree. Yeah, and then lastly, we want to take the results from this to build textual rules that are readable and understandable by users and domain experts. We implemented this approach using Python and then evaluated it on 2 data sets. First off, we took the logistics example that was introduced as running example. That was a synthetic data set with about 5,000 instances. And the resulting decision rule was if the temperature is above or equal to 26 degrees for 4 or more measurements, then the class is not okay. So we can see that this accurately depicts the underlying ground rule that we mentioned in the beginning. So that's pretty exciting that it's such a good outcome, and it's also reflected in the accuracy, which is at 100%, meaning that we also have 100% precision for okay and not okay instances. Yes, and then we, of course, also wanted to apply this onto a real-life data set. That was a little bit more challenging because, of course, I think you all know it's not that easy to find appropriate data sets, and especially if we wanted to have a decision point, we wanted to have time series data influencing this decision point and being available, and some ground truth where we compare our results to. But we were able to find one from the manufacturing domain. This is about the production of this piece here, this workpiece here, which is called a valve lifter. And we can see the according production process, or rather the quality control process. So the workpiece is manufactured, and then we want to measure it to make sure it's okay. So the measuring process consists of the CAiSE measuring. This is a measuring machine, which is really fast. It takes a couple of seconds because it only measures the diameter of the silhouette of the workpiece. However, it is not that accurate, so it isn't able to identify all not okay pieces. So to provide good quality, a second measurement task is introduced called microview. So the measurement is being done with a microview machine, which is much more accurate, but it takes much longer. So it can take up to 8 minutes per workpiece to do this measurement, which is, of course, very expensive, very time-consuming. So the goal for this process would be that at the first task, the measure CAiSE task, we can eliminate as many not okay pieces as possible, so that we reduce the time consumed in the measure microview task. Yeah, so we applied our algorithm, and the rule found is if the diameter in the second interval of 5 has a percentage change of over 16%, then it is not okay. So it's an interval-based decision rule. And if we look at the time series data, so that's the diameter measurements for the workpiece, and it basically starts, I don't know, can you see the mouse? Yes, so this part here refers to this part in the beginning, then we can see the drop in values that refers to this middle part, and then it goes up again and it drops, and the lower values refer to this long part at the end, and the last values where we see the spike, that's not part of the actual workpiece anymore. That's where the robot arm holds the workpiece into the measuring machine. So if we look at the decision rule, we can see that the second interval is interesting. So it's probably around here, and if here we have too much of change happening, then it's probably not okay. And this could refer to the fact that it's possible to have chips on the workpiece, especially at this part of the workpiece. And if we do have chips, then we know the workpiece is not okay and we have to discard it. Yeah, so overall the accuracy is about 91%, but what's really exciting is that the precision for the not okay pieces are at 100%. Meaning that at the first decision point, every workpiece that is labeled not okay and is discarded is truly not okay. So that was basically the whole goal of this, that we can eliminate as many not okay parts as possible. Yeah, let's move on to the next slide. So just to sum up, I presented EDT-TS, which is an approach that allows to discover decision rules that are based on time series data and to build interpretable decision rules from that. The evaluation showed that we can achieve high accuracy and high precision using this approach. However, of course, we have some limitations. So right now, the approach is not taking into account any kind of noise. So we have not a robust approach so far. And in addition to that, the computational complexity can get quite large if we have multiple time series data, for example. So that has to be optimized as well. Yeah, as mentioned beforehand, availability of data is always an issue. However, especially in this case, I think it's not due to the lack of data overall, but I think a lot of use cases have, for example, external sensor data that has not been integrated into the event log so far. So I think we can work on gathering more data, integrating additional data into event logs to provide more usable data. Yeah, and for current work, of course, I'm trying to work on these limitations, but I'm also looking at how different time series can interact. If we have multiple time series in an event log, are there interactions, and if so, what does it tell us about decision rules, for example? How can we work with that? And yeah, another big focus is also runtime decision mining, so meaning while an instance, while a process is running, we want to mine decision rules, and with the special focus of taking time series data into account, because that brings about a couple of interesting challenges, so about setting window sizes, for example, or how to integrate this time series data into the event stream. So I think it's a quite interesting topic. Yeah, that's it. Thank you very much for your attention.
Thank you very much. So I'm collecting already the first hands. So I think Ulrich was first, and I'm coming back to Max, and there was Johannes. So let's start with these three ones here.
Nice presentation.
Thank you.
I have a principal question.
Yeah.
If you describe decision rules, it is extremely important that you provide them with a justification, because you want to prevent people from doing bad things, or machines from doing things that are not appropriate. Now, your approach is focusing on sort of an inductive justification. You collect data from the past. And this approach is, of course, problematic for two reasons. First, what you collect from the past may be a reflection of, well, maybe even bad practice that you don't want to reproduce. And the second problem is, of course, that you want to avoid the problems of the inductive fallacy. So against this background, what are use cases where you think your approach is beneficial?
I think one point is that what was really important for us is that the resulting rules are interpretable. So that's one way we want to counteract that. So we don't immediately take these rules and put it into production. We want these rules to be then looked at by a domain expert to check, is it right, does it make sense before it is really used. So I think...
Sorry, but then you could right away ask them, what is the rule here?
Yes, but that's not...
all the work. I mean, that's what I would like to know.
I think on the one hand side, it's quite interesting to see what is the true rule, because I think oftentimes people think there's a decision rule and it's not actually used. So I think that's a very interesting use case to check, is it the same we think it is? So I think that's one of the very interesting use cases. Yes.
So it's about analysis more than about...
Yeah, sure.
So people might even call this not a decision rule, but a quality standard, right? So that is the basis then for taking decisions if standards are met. Yeah. So let's continue with Max. Thanks a lot.
Okay, thanks for your presentation. I was wondering about the intervals, and you say 2 times, 3 times the repetition. How you find out what the interval are? Because as long as it's just one single slope, then it's fine. But how do you determine that the interval finishes and the next one starts?
Yeah, that's a very interesting question and a challenging question as well. So we were thinking about that. And so we have 2 possibilities. The one is you can set the interval size manually. So if you have some hints in a specific use case and what could be useful, you can set it manually, but generally we automatically apply, I think, 5, 10, and 20 intervals. So that's what we use for all use cases, that we split it automatically in these intervals.
Please go ahead, yeah.
I think my voice is good enough. So it's not adaptive, meaning the intervals are fixed.
No, not so far. Yes, but that's definitely a good approach. We were also thinking about adapting it, but not so far. Mm.
All right, so Johannes has a question as well.
Thank you very much for the interesting presentation. Have you considered any simple benchmarks for the accuracy and precision? For example, just taking aggregates over the time series and using that to classify. And then perhaps a second follow-up question. If you would use, let's say, deep neural networks that do all the feature engineering for you and then apply some post hoc explanation techniques, do you think that that would be a valid alternative? Or will these processes always be, let's say, relatively simple so that you can do this still in your way when there are, let's say, relatively straightforward relations?
Yes, we were also thinking about applying explanations post hoc, and that's definitely something that we are also working on. But I think in this case, so I was looking at some of these methods, and a lot of them involve visualizations, and we did not want to include some visualizations. Our goal was explicitly to have some form of stated decision rule at the end that we could compare. But of course, that's also a very valid approach, and I guess that's also very interesting. So maybe we will apply that in the future as well, in addition to this approach. And the first question, sorry, can you?
Where you benchmarked with a very simple aggregation instead of your rules over the time series?
No, we did not do that.
All right, so Jochem, final question.
Thanks for the honor. Thank you very much for the very nice presentation. You mentioned in your conclusion slides that it's a very challenging problem to store that time series data in an event log. So do you have any tips or insights regarding how you would accomplish that feat? Especially, I mean, you talked about IoT environments, about like multivariate environments where you have more than one time series compared to what you do in the experimental evaluation. So any insights, any tips on how to achieve that kind of goal?
I don't know about tips. So for the manufacturing use case, we were lucky enough that each measurement event was an event, so each measurement task was part of an event, so it was already part of an event log. But yeah, of course, that's a challenge, and I'm currently not working on it myself, but I have one of my colleagues in this department is actively working on this topic, on how to integrate sensor data into event models and how to use this information in a useful way. So yeah, I'm sorry, that's all I can add to that.
So we have one final short question, as Manolo promised.
Well, thank you for your talk. It was very interesting. So my question is, sometimes you don't have like regular measurements for some elements. For instance, in a healthcare a scenario in which you measure the temperature of patients, it's not exactly in a regular interval. So it might be difficult to compare the time series of one patient, in this case, to the other. Have you thought about this challenge?
Yes, I have thought about it. It's not integrated so far in this approach, but yeah, there are, of course, methods to try to what's it called, dynamic time warping, for example. That would be a technique that you can use to set it into the right context and to be able to compare measurements that are not exactly on the same level. So that would be one further optimization of the approach. So yeah, it's definitely interesting and definitely also a challenge. So there are lots of challenges that we still have to address.
Right, Beate, thank you so much for your talk.